So good afternoon or good morning, depending on where you're joining us from, everybody. My name is Jesse, and I am with Exploring by the Seat of Your Pants. If you're joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world through live, free, interactive broadcasts. And we are continuing on in our final day, it's kind of sad, of our Week of Wonder. So we have been joined by the Canadian Association of Science Centers coast to coast to coast in celebrating and showcasing their just incredible virtual offerings. Science centers are opening up again all across Canada. So if you get the chance to go in person, they really are the most amazing places to learn about the world and cosmos. So before I dive in with today's talk, we've got an interesting tech issue today. It was going so smoothly the entire time I got spoiled. And so we need to highlight something a little bit for our live groups and for our YouTube groups today. So you'll be able to hear the TWOSE World of Science Edmonton team. Great. You're able to hear me. Great. None of them they can't hear any of us. And so what that means is when we go to Q&A, you guys are going to be able to type questions in the chat bar on YouTube. That's very easy. For our live classes, there is a chat on the side of your screen. You'll share questions there. I'll put them up in a banner so that the Edmonton team can see them, and hopefully it goes as smoothly as possible. In any case, we're going to dive in with today's topic, which is weather reveal. We're going to learn a little bit about the amazing weather and climate that really does shape our lives and increasingly does so as climate change has become such a big issue around the globe. So I'm really excited to dive in, do some really exciting demos, learn a lot together, and blow some minds. You guys are ready with me? Let's buckle up, dive in, and take it over to the TWOSE World of Science Edmonton team. Thanks so much for joining us today, guys. Take us away.
All right. Thank you very much, Jesse. Welcome, everyone. And I want to thank you all for inviting me into your classrooms today. And I want to thank the Canadian Association of Science Centers for helping us put this on. We're a member of the Canadian Association of Science Centers, and this is my first time to get to present like this. So we're very excited to talk to you today about weather and climate and how they're related. And I have 3 different demos today to help us see some of the parts of the weather that are usually invisible. But before we get started, let's talk a little bit about climate and weather and how they're different and how they're related. When we're talking about the weather, it's the atmospheric conditions outside right now. What's the wind speed? What's the temperature outside? Is there any precipitation of any kind? So when we think about the weather, we're thinking about the conditions in the atmosphere right now that surround us. When we're thinking about something like climate, we're talking about the weather over a long period of time. And in Canada, we have a very varied climate. For example, on the eastern coast, we have a city like Halifax, is a maritime, eastern maritime climate. It's a little bit cooler, and they have about 100 days of fog every single year, as opposed to a place like Hamilton in Ontario, where the climate is a little bit cooler, and cooler in the winters and a little bit warmer in the summers. Here in Alberta, where I live in Edmonton, we have pretty cool winters and very nice dry summers with long sunny days so we can enjoy time and be outside in nature. However, if you move north to a territory like Nunavut, the climate is very different from what we experience here. It is an Arctic climate in the Arctic zone with bitterly cold winters and even very cool or cold summers. And lastly, if we look all the way west at Vancouver, they have a little bit of a different climate because they have some shelter on the eastern side from the Rocky Mountains, and they have some warmth coming in from the Pacific Ocean currents. So they have a little bit milder climate with more rain than we might see here in Edmonton and Alberta. Now, how are the climate and the weather related? Well, this summer, we saw examples of it being a lot warmer here in places in Canada than it normally is. And if this happens over a longer period of time, how does this affect our day-to-day lives? So the first thing we're going to talk about today is wind. So when we're thinking about wind, we can feel the breeze blowing, but we can't always see it. And so let's think about how wind is created. Wind is created on large scales and small scales. And the first thing I want to show you is the large scale with this globe that I have. We can see here around the equator, this is the band of the Earth that gets more sunlight than other parts of the Earth in the year. So this air around the equator of the Earth gets heated up, And as it warms up, it expands and begins to rise, because as it expands, it becomes lighter or less dense than the air around it. As this air rises and begins to move north, the cold air around the polar regions doesn't receive as much sunlight, so this air is colder. And as the warm air moves north, the colder air moves south and creates large areas of wind. These are large winds that we have across the globe. However, wind is also created on a smaller scale. And to see the smaller scale, I have our first demo of the day, and I would like everyone to check this out. Okay, let's think about the wind. Can you smell the wind? Can you feel the wind? Can you see it? We might see the leaves flutter on the trees, but have you ever actually seen the wind? I've got 2 boxes today that are going to help us do just that. Can you guess how these are going to help us? My first box is filled with ice. My second box is filled with soil, and I have a pair of hot lamps shining down on it. And I have them connected by this clear tube. Do you have any guesses as to how this will help us see the wind? One of the ways that wind is generated on the surface of the earth is when the earth is heated unevenly. Like my boxes here, the one on this side is going to be heated a lot more than the one with ice. Just like in the real world, if you had a snowbank next to some asphalt, the dark asphalt would absorb a lot of heat energy, whereas the snowbank would reflect more. So they would be heating unevenly. So in this box, we have the dark colored dirt is absorbing a lot of heat energy. So the air in this box is going to begin to warm up and move more rapidly. As it moves more rapidly, the air molecules spread out and become less dense. So that means they are lighter than the air around them. So the air in this box will begin to rise up into the atmosphere, in the same way that a hot air balloon or a paper lantern begin to rise up. The ice in this box will cool down the air around it, and those air molecules will move more slowly, and they will begin to condense, and the air in this box will sink. Think about the basement in your house. It's often the coolest place because the air that's the coolest sinks down low into the basement to fill up that space. So we know what's happening to the air in this box and the air in this box, but what about the air in the tube? Is it moving or is it still? How can we tell? Let's add smoke into the cool box and see what happens. Can you see the smoke? Look at the tube. Now the air is moving. We can see it because the air is carrying the smoke with it. It's moving from the cold box to the box of warmer air. And as the smoke enters this box, you can see it rising up into the atmosphere, just like we talked about, because the air in this box is less dense because it's being heated. What do you think would happen if we put the smoke in the box with the heat lamps? Is the smoke going back through the tube? No, it's all rising up into the air because this air is warmer and less dense than the air surrounding it. So today, we've seen one example of the way that wind is created on the surface of the earth through uneven heating. What do you think is going to happen to this warm, moist air that's rising into the atmosphere? It's going to make a cloud. Let's see how that's done. All right, welcome back, everyone. Before we get to that cloud, I wanted to mention a couple of other things about wind. The first being, sometimes winds are very consistent and they get special names in different parts of the world. For example, here in Alberta, we have a wind that comes from the west and rises over the mountains called a Chinook wind. And this wind, when it blows down the eastern side of the mountain, it can rapidly change the air temperature to the places it's blowing. Up to about 20 degrees. However, once in a town called Pincher Creek on the eastern side of the Rockies, the temperature rose from -19 to +22 degrees in 1 hour. So they saw a change of 41 degrees. So while we can't always see the wind with our eyes, we can measure it and we can learn to tell which direction it comes from. So observation with our eyes and being out in our own environment is the best way to observe our local weather. So now, we had some warm, moist air rising up into the atmosphere, and we said we thought it might make a cloud, but we can't go high in the atmosphere. So let's do that here at ground level. I have some special tools and instruments to show you and we'll make a cloud right here in the classroom. The first thing I have is a large, heavy-duty glass bottle. This is called a carboy, and the sides of it are very thick, and it's going to hold a lot of air for us, and this is what we're going to make our cloud in. I also have a bicycle pump with a cork on the end of it so that I can seal the top really tightly here. I'll talk more about why that's important soon. And lastly, I have a tray with some water and a few matches. Now, how are these pieces going to help? Well, in order to make a cloud, in order for a cloud to form, the water vapor that we just had rising into the atmosphere, it needs a couple of things. It needs to cool down and condense, and it also needs particles high in the air to collect around, maybe particles of smoke or other kinds of dust. So all the pieces I have here are going to help us recreate those conditions today. So the first thing I need to do is switch out my glasses to safety glasses as we work with some high pressure items here. So put on my safety glasses, we're ready to go. The first step is to add some water, just like we would have high up in the atmosphere. So I'm going to add about a tablespoon of water to my carboy. And we want the water to be all around inside here, so I'm just going to pick it up and turn it so that the water is coating the walls. And we can see each other really clearly. Keep this in mind soon. We'll see what happens. Now, we also mentioned that we need some particles of dust or smoke in the air. So for that, I have a pair of matches, or I have some matches that we'll use today. And then as soon as I drop the matches in, I'm going to plug it up so that we contain the smoke. There we go. All right. And now we have all the elements we need to make a cloud. We have the particles of smoke inside, we have the water vapor inside, and now we need to manipulate the pressure. And to do that, I'm going to use the bike pump to increase the pressure. I'm going to put more air inside this bottle. And as I put more air in, the bottle gets full and the molecules begin to move around rapidly and bump into each other and ever so slightly heat up. And that heating up action is what we're going to use to help us make the cloud. Because when I take the cork out of the bottle, the air inside will cool down rapidly, which we know is going to make the water molecules condense on the smoke, and we should have a cloud formed inside. All right, my friends, I'm going to count down from 3, and let's see what happens. Here we go. In 3, 2, 1. What do you think, my friends? We totally achieved. This is the best one I've done in a very long time. I don't even think you can see me. So let me contain some of this and ask some questions. We made a cloud by increasing the pressure and then decreasing it rapidly. What do you think will happen inside the bottle if I begin to increase the pressure? You can still see a little bit of my cloud here, so make a prediction. What's going to happen when I increase the pressure inside of the bottle again? Well, let's find out. So look at the bottle. It looks like it's becoming transparent again. Every time I pump a little more air in, it heats up a little bit, and we lose the cloud. Do you think it'll come back? Let's see before we move on to our next piece. Exactly. Perfect. So we manipulated some conditions that normally happen way high up in the atmosphere to create a cloud inside of a bottle at ground level. We changed the atmospheric pressure so that the bottle got warmer, and then when we released it all at once, we cooled it down rapidly and saw a cloud form in the bottle. If we're thinking about the clouds in the sky, this would be formed similar to a cumulus cloud, which forms when the temperature decreases and water condenses on small particles in the air. Now, let me put this out of the way. We'll get ready for our final demonstration here, where we're going to talk about something else that's really usually invisible to us, and that is air pressure. We looked at how wind was created, and we talked a little bit about pressure when we talked about some of our other cities. For example, when we think about the cities Vancouver and Halifax, they are close to sea level, so all the air above them is pressing down upon them very heavily. Whereas here in Alberta, we're about 700 meters above sea level, so that means there's less air pressing down on us. And when we talk about air pressure, we're thinking about all the air above us that is pressing down on us all of the time. I don't feel it. Do you feel it? We don't feel air pressure because we're constantly under the air pressure, and the air inside of our bodies is also pressing back against that. So the air in our lungs and the air in our bloodstream is pushing outward, while the air all around us is pushing down on us. So in order to see that today, I have a fun demonstration where we're going to see the effects of air pressure. So let me show you what I have for you. You need a little bit of extra safety equipment for this one. All right, so I have a blowtorch. I have a bowl of water here. This is cold water that I'm using today. Had some ice cubes in it earlier. I have a pair of tongs. We have our aluminum can. And finally, again, a little bit of water. So when we're thinking about air pressure, just like on our bodies, the air is pressing down on this can, but we don't see anything happening. And that's because inside this can is full of air also. So right now, there's air pressing down on the can from the outside, from all directions. And on the inside of the can, since it's also full of air, it's pressing back. And that keeps the can in this shape. However, we can manipulate this a little bit again, because I'm going to pour in about a teaspoon of water into this one. And this time, make sure there's enough in there, friends. This time what we're going to do is we're going to use a blowtorch to heat the water inside until it becomes water vapor. Then once we have water vapor and this entire can is filled with steam, then there's no pressure pushing out on it. So I'm going to take the can once it's full of steam and dump it in the cold water, and let's see what happens. Let me get the rest of my safety equipment on here, my friends, because this one has a blowtorch. There's that. Okay. So we're going to heat the water in the bottom of the can, and I'm keeping the can moving so that I don't burn a hole with this powerful torch in the can anywhere. Now we're going to listen very carefully to start to hear the water boil. Once it boils, we want to make sure that all of the air gets forced out and is filled with steam. Oh, now I can really hear it boiling. Start to see it coming out of the top some. All right, my friends, here we go. We have the small bowl of cold water in front of us. Count down again with me with 3, 2, 1. And look at that. Turn my torch off here. Can you see what's left of the can? We were able to crush it because of the air pressure in this room. I filled the whole can with water vapor, but when I turned the can upside down into the water, all that vapor cooled off very rapidly and condensed back into liquid water. That meant there wasn't anything left taking up space in the can. So the air pressure in the room is what crushed my can today. So now it's cold, cool, so y'all can see that. Excellent. So yeah, when we're thinking about air pressure, we mentioned how your elevation might matter. Air pressure is also an indicator of sort of longer term weather effects. And when we watch the temperature, we can read it right now and see the wind speed right now. But when we think about air pressure, we're often thinking of how does the air pressure change over a long period of time. Other times, for example, when big storms are coming off the eastern seaboard, like Hurricane Larry that came in, we were able to understand a little bit more how it might behave by studying the air pressure that was the low air pressure that was in front of the hurricane. So, all right, my friends, thank you for joining me today at the TELUS World of Science here in Edmonton to talk about some of the invisible aspects of weather. The first thing we talked about was the wind. We used some smoke and uneven heating to show how wind is created on a small scale and then on a large scale. In our second demonstration, we made a cloud in a bottle manipulating air pressure and putting some small particles of smoke inside. And then finally, we crushed a can using the force of air pressure that we're all feeling all the time. So thanks a lot for joining me today, and we'll get to your questions here soon.
Fantastic. What a neat demonstration. I've never seen the can one before. The other two I've seen in other things in the past, but the can is really unique and what a great opportunity to highlight some cool weather in action. I'm so glad you guys can hear me too. This is great. And so we can dive in with a better Q&A group. We got a whole bunch of 4 classes live with us. We've got groups joining on YouTube from all over Canada. So welcome into you folks as well. What I want to start with is Madame News class. If you guys want to kick it off, they were so enthusiastic at the beginning. They were yelling so loud that they couldn't actually hear me for the enthusiasm in the class. So I think they will have kept that going over your demos today. And I want to bring you in for our first question. Madam News class, come on in.
Harriet, do you have a question? No questions for right now, I don't think.
That's okay, guys. We can come back in just a second. Let's head to our Richard School secret grade. Our class there. We got 2 classes at the join us. 5, 6s. Hi, welcome in. You guys are the fastest wavers ever. Come on up. Do you have a question for us today?
Did anybody have a question? Lovely. Thanks so much.
How come the air pressure around the pressure around the can kind of collapse? So the can.
Oh, we got some epic reverb. Why is that going on?
So I think
my friend at World Science.
I don't know. She was just going to ask
Thank you.
if you could explain a little bit more about how the can crushed, like how the outside caused the can to crush.
I thought we were going to get questions on this. So tell us more about that can. What's going on? I mean, I know you explained about air pressure, but it really is hard to wrap your mind around if you're new to this concept. So anything you could explain more would be great.
So it sounds like you're asking a little bit more about what happened with the can, right? Yeah, so let's see. I have another one right here, so we can look at them sort of side by side. So the thing we need to think about right now is that inside of both of these is air, just like that's on the outside. I cleaned them and I washed them beforehand, so we emptied all of the fizzy water out and we filled it with air so that it's just like our bodies, feeling all the pressure all the time. The thing that we did this time, though, was we removed all the air from this can. And that's what I was doing when I was heating it up with the water. I was boiling the water to fill this can with water vapor instead of air. And as long as I was boiling the water, it was filling the can with vapor. I could see the steam coming out of the top. However, when I put this bowl, used to have ice in it, so the water is cold, and that was really important to helping the things too. When I put the can upside down in, I am very quickly cooling all of that tablespoon of water off, and it converts from steam back into liquid water. So now there's no steam on the inside, there's no air on the inside, and so there's nothing pushing back out against the walls of the can like there are in this one. And that's why as soon as the water cooled down rapidly, the outside air pressure that we're feeling right now, you're feeling it in your classroom, I'm feeling it here inside the TELUS World of Science. It pushed in on the can once the water vapor left, because then there was, I don't think technically there's a vacuum inside, but there's not very much air inside. So with no air pushing back out, all the air pressure in the room crushed the can down to this size.
Yeah. I guess the closest analogy that some of our kids at home might know is if you've ever dove deep into a pool, you'll notice that there's a pressure that you feel as you go deeper and deeper. Same principle, we just feel it more in water. With air, we're really attuned to it, and we have this pushback, I guess, built into our bodies. And so a neat illustration of that today. Guys, if you want to answer.
Drive around and our ears pop, so yeah.
Yeah, excellent. Ms. Erlinson's class, Diego on YouTube wants to know, just as a follow-up question, if the same thing would happen with soda or another fluid. Is this just water that this is happening with, or is it anything?
My guess would be, my hypothesis would be that if I had a cool fluid, like if are you talking about boiling the liquid in the can?
I don't know. I mean, I think that's the idea. If we did the exact same thing with another kind of liquid, would it be the same result?
If there was enough water content in it, like something like tea or coffee or even like soda, I imagine that once you get it boiling, then yes, you might have some other things burn off of it. Some of the sugars might burn up and smell really bad while you're trying to do the experiment. But as long as there's enough water content in the liquid that you've chosen to fill the can with the steam, then you should be all right. It should work. but I would be very careful testing other liquids because you don't know what is in them. I think water is probably the safest one to use.
Yes, and you had a lot of safety equipment on, and this is something we always like to illustrate with science demonstrations, that have a trained professional there, really know what you're doing, do it with a parent for sure. Some really, really neat stuff to learn, but safety first. All right, let's head to room 7. If you guys want to unmute your mic, come on in. In fact, all our teachers, unmute your mics. We can only hear you when we bring you in. Hey guys, welcome in.
No, thank you.
If you wanted more than just a little bit of water, would it still work?
If the question should, like, if we added more water or less water?
Like if you filled half of it with water, would it still work?
Yeah. So if you fill it up even more, would it be the same effect? You blew their mind with this, man. This is exciting.
No, these are all great questions. Notice that I wanted to only put just a small amount of water in there, and that's for a couple of reasons. Imagine if we filled the can halfway with water, and my blowtorch is off so I can show you safely here now. It would take this blowtorch a lot longer to boil this amount of water, half of the can. So the change would be that I would need to heat the water for a lot longer time to get it to that same boiling pace. And don't forget, also, if we had that much water, the can is now half full of water and half full of steam. So what do you think would happen when I turn it over and all the water hasn't boiled out? Because that was an important part of my activity, was boiling off most of the water to make steam. But if we filled it halfway, I'm not sure I could boil all that water out. So something else would be pushing against the sides of the can besides just the steam. And it might not get crushed as much if we filled it up all the way.
Yeah, we want to have the maximum possible crushing power.
So it might burn a hole in our can if we tried to put the blowtorch on it for that long. So that's a great idea, but we would need a more durable container to hold our water and see what happens. But I will say, I've seen this demonstration done with like a 50-gallon oil drum, because the same principle holds. The pressure pushing down on us that crushed this can is the same pressure that can crush an oil drum. So yeah, it's super powerful and really neat. Thank you.
Very, very cool. Great question, guys. All right, Gage and Corbin at home, unmute your mics. Come on in. Got some homeschoolers joining us today, and want to bring them in. Hey, guys.
Say hi.
Hi.
Do you have any questions?
I have a question. With the cloud thing, how does that happen naturally?
How, the cloud, is that what you were asking, sir?
Yeah, with the cloud device that you're making, how does that happen naturally? So, like, how would you get that same effect, but in nature?
Oh, so the same effect, but in nature. So it's a combination of a couple of things. Remember, we mentioned air pressure. The higher up you go in the atmosphere, the less the pressure is, because there's less molecules above us. So when there's lower pressure in the atmosphere high above us, the air is cooler, okay? And in the same way that we cool down the air unnaturally with a bicycle pump and pressure, the air above us is cooler, and that condenses the air, the warm, moist air that rises up, that condenses high in the atmosphere because it's colder. And there will be small particles of dust or smoke high in the atmosphere also for them to form around. Clouds form at lots of different levels and layers in the atmosphere. So there's so many different clouds to talk about. We could do a whole presentation just on those kinds of clouds, because the one I made today is similar to a cumulus cloud that you might see in the sky, but it wasn't like those beautiful long and wispy clouds. It wasn't very dark and thick like you might see from a thunderstorm. So the same conditions I created of low pressure and cool air is what helps the water vapor condense around particles in the atmosphere.
Yeah, very cool. And a nice follow-up question right on YouTube from Mr. Roseclass. So Abdallah at Queen Elizabeth Public School joining us in Ottawa. He wants to know, why are clouds white? What's going on with that?
Why are clouds white? Let's see here. Snow? Okay, so y'all can't see this, but fortunately behind the camera, we have a resident weather expert, Joel Weatherly, here helping me. And he says it's because of the way the light scatters when it hits the clouds, the sunlight. So.
Yeah, it's a little, I think the science of it gets a little complicated for kids that are in younger grades, but it's very, very cool. And of course, when you're at night too, or when you're at sunset or sunrise, you get that slanted effect where it's spreading off particles in a different way. And so you end up with yellow and red and purple clouds. Cloud color science is really, really neat. As you guys get older, certainly into middle school and high school, you'll start to learn more of this. I'm so glad we got that question. All right, Guru on YouTube has a question, and then I'm going to head back to our grade 5 at our news class. So Guru wants to know, can you reverse the experiment with hot water on the outside and cold water on the inside to make the can explode?
So this is a wonderful idea. Let's think this through. You want to set up an experiment where we have, you said cold water on the outside and warm water on the inside. And we want to warm up the water on the inside to see if we can make it explode again to take up all that space.
So hot water outside, cold water on the inside. I guess the principle is you reverse it, and instead of imploding or crushing in, would it blow up?
Oh, okay. I see what you're saying. So yes, I think the inverse wouldn't. What we would try to do is, if we were heating the water again, is to get the water. I think we would want to put water in here that we were going to heat again, so that the steam would push the walls back out as we heated it. But this vessel is not really in good shape. And another challenge with something like this is once we've crushed it, I can see some small holes in it. So our water wouldn't stay in it the same way. But I think we would. Now, if we had a fresh can and we put cold water in it and it was in water warm on the outside, could we explode it? I feel like we would need to somehow heat the contents in here so that it would expand outward. And another challenge would be that the top is open. So anytime I did something to create expanded air or the steam, some of it was able to escape.
Yeah.
So if we were able to seal this up somehow and then heat the contents inside, we might be able to expand both either the air or the water inside to make it explode. That might be an interesting experiment.
We'll have to do a second follow-up.
I love that.
Yeah, make that happen, guys. All right, let's let our news class. Come on in. I know you typed a question in the chat, but way more fun to come and say it on screen. So go for it. Hey, guys.
Hello. Actually, okay, so we might have 2 questions.
Let's do it.
So the hot air rises is something that we've learned, and it's true, and we've observed that. But we were wondering if there's a point in the atmosphere where that is no longer true, and why would that no longer be true if hot air doesn't rise?
That was my question.
So is there a point in the atmosphere where hot air no longer continues to rise? Okay, so a couple of things to think about. Even our warm rising air eventually is going to be affected by gravity. So we know that's going to happen. And as it warms up, it's going to encounter either other masses of cooler air, and that could have an effect on it. So Joel, what do you think? Is there anything else that I'm missing? Or?
As long as it's warmer than the surrounding air, so if it's less dense than surrounding
there you
air,
go.
it's
Yeah.
still a density. But
So
the temperature in the atmosphere cools down to a point, and then it starts to warm up again.
got it. So Joel, I'm not sure if you can hear him, but Joel has mentioned that it is specifically about density. One thing we mentioned about warm air is it's less dense than the air around it. So as long as the air surrounding the warm air is less dense, the warm air will continue to rise. Now, the other point that Joel mentioned was as the atmosphere rises, it cools off, and then it gets to a point, and then it stops cooling, and the temperature begins to rise again. So warm air will continue to rise as long as the air surrounding it is cooler than the warm air.
Great question, guys. By the way, I love the fact that when we dive in with questions, we're taking expert advice from all over the place at the TELUS World of Science. Some of the questions are stumping. Like, this is the essence of science. You know, you guys are highlighting these queries. Science is ever in development. You know, more people are learning things every single day. And so I love that we can highlight this with our inquiries today, guys. Madam New, you had a second question. I'm going to come back to you and go through all our live classes. YouTube folks, still lots of room for you guys. We are whipping through these. This is great. So come on back in, Madam New.
Okay, Fiona, can you ask a question? Shout it out, please. Shout it. Yep, go ahead.
Sometimes the clouds will cover the sun. So how come the clouds won't melt?
Okay, how come clouds don't melt?
Yeah. Or burn off, I guess. So with clouds, why, when it's really sunny out, which it is all the time. So if you're right on the equator, you've got some clouds, what's stopping the clouds from just dissipating? Or do they do that already?
So one of the things we can think about is that clouds are made up of so many small particles of dust that they're floating high up in the sky, and they don't melt, because technically a cloud is not totally a solid. But what you're talking about with it burning off and mentioning fog, as the temperature rises and the sun comes up in the morning, when you have a cloud at ground level like fog, it can warm up and have the effect of burning off the fog. And then the first part of your question was about clouds higher in the atmosphere, though, and why they don't always burn off. And then, Joel, can you help me with that one, or was there anything more specific?
It's about getting the conditions just right.
Mm-hmm.
We can have it where the sun heats up the ground and we can have changing conditions. So
Yeah.
we don't have it ideal for a cloud anymore. But if it's still just right for a cloud, you can have them in the sunniest of days.
Excellent. And Joel's mentioning that depending on the conditions, clouds can hang around for a long time, even on very sunny days, which is what we notice here in Alberta, because we have lots of long sunny days in the summer, and we might still see some puffy clouds floating around because up in the atmosphere, the conditions are still right for them. As they move across the country and change positions and the temperature rises or falls, then they might dissipate or change, and we might not see them anymore. And again, I want to back up what Jesse said, and I'd love all these questions, and the ones that we don't always know the answer to leads us to do new experiments and new activities. And I think we almost get to learn more from the questions that stump us than the ones that we just happen to know the answer to, or I have an expert here to help me with. So thank you.
Yeah, I forget which scientist it was, but it was the quote that, we learn more from, that's funny, than we do from eureka. Like, things that really challenge us they do drive a lot of new inquiry and a lot of new science, which is fantastic. And so, great, guys, this is awesome. I want to note, too, we've got Miss Erlinson's class is joining us in New Mexico today. I've been to New Mexico. Talk about a place where it gets so hot the clouds burn off. Arizona, New Mexico, that is quite the part of the world. So it's nice to have a diverse audience today. Richard Secord, come on back in. So all our teachers, unmute your mics. We can't hear you till we bring you back
Thank
in.
you, Morgan.
Go for it, 5 6s.
I have a question. How did the clouds form so quickly in the jar?
Yeah, how do they form so quickly in the jar?
Oh, in the jar. Yeah. So how do they form so quickly in the jar? Because I used the bicycle pump to add a lot of extra air here. And you saw me, it took me a minute to pump all that extra air in. But then what happened was I released it all at one time. So it was able to all flow out very rapidly. And that is what cooled down the bottle very quickly. So I was able to do that because I let all the pressure out all at once. Normally, this would take longer time higher up in the atmosphere, but here we're able to do it very quickly because we're able to seal the top off. Let me show you the cork that I have. This is not my normal bicycle pump. You can see that here, there's a small cork right around the top, and I used that as soon as the matches went in to seal it here. And this seal is very important for this demonstration to keep the air contained before we let it out very rapidly. And when I did that, you could hear it rush out very quickly, and that's when we could see the cloud being made because the temperature dropped so rapidly. It's all about manipulating the temperature and the air pressure inside of my carboy. So
this is the thing, both of this demonstration and at science centers in general, you can see all these amazing principles in action. That's why I encourage you. We've got a lot of Edmonton classes today, which is awesome. So you get the chance to go to TELUS World Science, please do. It's an amazing facility. Wherever you're joining from across Canada and the US, head to these amazing places. Again, you can learn so much, have a great time while doing so. It's the essence of what the Week of Wonder is all about. All right, time for 2 more questions. Time flies when you're having fun, man. Room 7, let's come back to you guys, and then Gage and Corbin, you can wrap us up in just a second. Hey, Room 7, welcome back. I like the straight up hand. Very enthusiastic. Unmute your mic, though. Then we can hear you guys. All right. First choose and go from there. While you're doing that, I'll just bring up TELUS World Science.
There you go. All right, go on. Go on. That's enough.
Yeah.
So when the cloud happens so rapidly in the jar, could that also happen high in the sky?
Yeah, so is there ever a situation where the cloud happening so rapidly happens in the sky? Is it ever happen in nature, or is it only because you've got such a controlled system there?
Fairly quick cloud formation. Doing it here is way faster.
Yeah. So clouds can form fairly quickly, quicker than we might think. And I'm thinking of places like when in San Francisco, when the fog really rolls in the mornings and things, but it doesn't happen as quickly as we manipulated it here. So it doesn't always take a really long time and they gather and form slowly. they might form faster than we could imagine or think they do, but they certainly don't form at the same speed as what we did here, like with the finger snap, because again, we manipulated all these variables with the pressure and the temperature with the bike pump. So it doesn't happen quite that quickly, but it's also something that doesn't always take a really long time. So clouds can form pretty quickly, yes, but not as quickly as we did today.
That was a pretty fast answer. So we'll take a couple questions, actually, one from YouTube as well. And I want to note San Francisco, great choice as a foggy place. They actually named their fog in San Francisco. It's called Carl, and it's an amazing fact. Let's head to Lily. Martin, Mr. Detto's class, Queen Elizabeth Public School. You guys have been joining us all week long. Welcome back. Lily wants to know, why does the wind make sound? I love this question.
So why does the wind make sound? Well, the wind itself might move the trees or rattle them on the breeze, but sometimes I think what you might be saying is like the whooshing or the vibrating sound. And as the wind is moving through the air, it is vibrating and pushing the particles around to create that pressure wave that creates sound that we hear. Usually I hear it a lot when I hear something banging around, or like I said, the leaves on the trees, but the wind itself can make sound just because of the vibrations that it causes as it moves rapidly through the air. So yeah, as it pushes against our inner eardrums, we hear that and perceive it as sound. So it's just the way that the wind is moving, it's creating its own sound as it pushes through the air.
I think it's the ultimate manifestation of this idea that air, it has substance to it. We were talking about hurricanes and tornadoes yesterday in a program. So, I mean, hopefully none of us have experienced one of these firsthand, but if you've ever gone out in a very stiff breeze, you'll hear the wind because it's powerful. You'll feel it. You have to walk into it with a slant. I mean, it is powerful stuff, air. And I think this whole presentation has illustrated that so beautifully. All right, guys, Gage and Corbin, come on in for one final question. We'll wrap up from there. Unmute that mic and you're good to go, boys.
Okay, so with the cloud, if that happens naturally, then if it has an air compressed seal, does that mean the atmosphere is that air compressed seal making it so no hot air can escape, but it just travels further?
So you're asking more about like how they form sort of in the atmosphere when they don't have something like a cork to seal things in?
Yeah, since well, at some point when the spaceships and satellites went out into space, they had to break the barrier in that. Does it break it permanently, making it so clouds can't form as fast?
Interesting question. I like this one.
Rising up and how long it takes them to form, and is there some sort of like the cork on the top here helped me maintain pressure in the bottle? Is there some mechanism like that that maintains pressure over the whole Earth so that, you know, the things don't escape the atmosphere? So yeah, that's what I was going to say. When we're thinking about what keeps them in our atmosphere, and the pressure that the air molecules are feeling are all attributed to gravity. So just like I use the cork to seal it up, gravity is sort of the seal around the whole planet that draws all that air down towards the surface of the Earth. The air pressure is less the higher you go above us, but until you get to actually space itself, we have gravity pulling those molecules of air down towards the Earth, and that's what creates the pressure that helps the clouds form high in the atmosphere.
Yeah. And then just in the off chance this was the final little bit of that question for Gage, guys, when a rocket goes up, it does break the sound barrier. We have this with high-end planes as well. To my knowledge, there's no science to indicate that it permanently changes that area. It just resets the air molecules around that, allows you to have more clouds and so on. Is that correct? We've got Joel in the background too. That's correct?
The interesting thing, Jesse, after you mentioned that, is Joel is saying those kinds of high-speed vehicles traveling through the atmosphere can create their own little clouds because of the intense pressure they create. So, yeah, they can create their own little clouds as they go through the atmosphere. Exactly.
Cool. Also, we talked about wind having sound earlier. So I used to be right under a flight route. Like I could basically touch the bottom of the planes coming into Pearson when I grew up. And there's incredible air sounds that come in the wake of those planes. They make all sorts of weird turbulence behind them. So if you've ever been close to a plane when it's landing, it's really freaky sound. Sounds like aliens are landing in spaceships. It's kind of neat. Guys, this has been so much fun. I love your interesting clouds. We've had more cloud questions than we've ever had in our history. So way to go, guys, for really inspiring a lot today. What I want to do again, really quickly before we wrap up, highlight, if you want to learn more, tellsworldofscience.edmonton.ca. So many amazing resources there, so many cool exhibits. Head in person if you can. If you can't, check out their virtual offerings. And of course, this is part of our epic Week of Wonders. If you want to see all these programs, every one of our 20 sessions is all on this page below. Hopefully you guys can check that out when you're done. Thank you so much for joining today. What we do at the end of every broadcast, we're going to end this one with two. Now that we got all that audio working, I'm going to bring in all our classes. So grade 5s, Richard Secord, room 7, Gage and Corbin, unmute those mics and join me in saying a big thank you and farewell to our team in Edmonton. Thank you guys so much.